Hello, my name is Lily Wall, and this is my presentation for Lab 1, Constant Velocity for Physics 2211. Here's an overview of what we'll cover: an introduction to the concepts behind constant velocity, a tracker analysis of an object moving at a constant velocity, a computational model that predicts the motion, a comparison of the results, and finally, our conclusions. To begin, we'll review some key concepts. According to Newton's first law, an object remains at rest or moves with constant velocity unless acted upon by an external force. Constant velocity means that an object's change in position over time remains the same. We also use Newton's second law, which allows us to update an object's velocity using the velocity update formula. The purpose of this experiment is to observe the motion of a rolling object, specifically a roll of string, and determine whether it moves with constant velocity. We assume no air resistance or friction and restrict movement to the x-axis on a flat surface. If our assumptions hold, the object's position should change at a constant rate. Here's the free body diagram of the object. At the start, an applied force sets the object in motion. Once moving, the only forces are gravity and the normal force, which cancel out, leaving zero net force. According to Newton's first law, this means the object should continue moving at a constant velocity. Here's the video we recorded of our object's motion. To analyze the motion, I used Tracker, a video analysis tool. By tracking the object's movement frame by frame, we collected data on position and velocity. The frame rate of the video was 60 frames per second, so each time step is 1/60th of a second. Here's a summary of some other key parameters. The object's diameter was about 4 inches. Its mass was 370 grams, the total duration of the motion was 1.64 seconds, and the initial velocity was calculated as 0.364 meters per second based on position changes over time. Next, using this data, I created a computational model using Newton's second law to simulate the object's motion. This model updates velocity and position step by step over time. I've included screenshots of my code where you can see each formula being applied. Here's a visualization of the computational model. The object's position is updated continuously to reflect motion at constant velocity. The position function is upward sloping and linear. Now, let's compare our experimental data with the model. Initially, the simulated and observed positions align well. However, after about 0.6 seconds, the observed object lags behind the predicted path. This suggests that the object was not truly moving with constant velocity, likely due to unaccounted forces. So, what caused this deviation? Several factors could explain the observed differences. First, the object did not roll perfectly along the x-axis, meaning some displacement was lost in the y direction. Friction and air resistance also act against motion, and these forces were unaccounted for. And calibration errors in the tracker tool and rounding errors also may have occurred. These sources of error suggest that, in a real-world scenario, perfect constant velocity is nearly impossible. Lastly, let's explore some additional questions. If we flipped the x-axis, the velocity would be negative, but the magnitude would remain the same. Can we determine the exact number of forces acting on the object? The answer is no. We know that gravity and the normal force cancel out, since there's no acceleration in the z direction. However, external forces like friction and air resistance always play a role. This highlights the important concept that only in a computational model can we achieve truly constant motion. Thanks for watching.